Today we want to talk about being a transformer. Shifts, reflections, stretches, and shrinks. Most of you probably remember that for a while transformers were very popular toys. Well, today you get to play with functions by transforming them. Let's talk about how that happens. First of all, let's talk about vertical shifts. Suppose I start with a function f of x, and I want to shift the graph of that function c units down, where c is a positive number. I can define a new function h of x equal to f of x minus c. The graph of h will be c units down from the corresponding points on the graph of f. If I want to shift the graph of f up, I could define my new function h of x to be f of x plus c. Let's look at an example. Suppose f of x is the square root function. F of x is square root of x. That would be this red graph here. If I define g of x to be the square root of x minus 2, the red graph would be shifted down 2 units to form the blue graph of g of x. The point 0, 0 on f would shift down to the point 0, minus 2 on g. The point 4, 2 on f would shift down 2 units to the point 4, 0 on g. If I define h of x to be the square root of x plus 2, I'm going to take the red graph, square root of x, and shift it up 2 units. So the point 0, 0 on the graph of f would be shifted up 2 units to the point 0, 2 on the graph of h, the green graph. The point 4, 2 on the graph of f would be shifted 2 units up to the point 4, 4 on the graph of h. Vertical shifts, I think, work very intuitively. Now let's talk about horizontal shifts. And for some students, horizontal shifts at first glance seem a little bit counterintuitive, but I think in a minute you'll easily see why they work the way they do. Again, we're going to let c be a positive number, and if we start with a function f of x and want to shift the graph of f c units to the right, our new function h of x would be f of x minus c. Replacing x with x minus c actually shifts the graph c units to the right. If we wanted to shift the graph of f c units to the left, we would actually have to replace x with x plus c and define our new function h of x to be f of x plus c. Let's see why that works the way it does by taking an example. Again, we'll start with the basic function f of x is the square root of x, the red graph here. If I replace x with x minus 2 under the square root sign, and that's my new function g, g is the blue graph here. You can see that it has taken the red graph and shifted it 2 units to the right. So the point 0, 0 on the graph of f is shifted to the point 2, 0 on the graph of g. If instead I replace x with x plus 2 under the square root sign, that is going to take my original function f of x equal to the square root of x and shift it 2 units to the left. So the point 0, 0 on the graph of f is going to correspond to the point negative 2, 0 on the graph of h, where h of x is the square root of x plus 2. So we see again that replacing x with x plus 2 actually shifts my original function 2 units to the left. Here is an example of a combined vertical and horizontal shift. I've started with f of x equal to the square root of x, the red graph. I've replaced x with x plus 2, which should shift it 2 units to the left. And then outside the square root sign, I've added 4, which should be a vertical shift 4 units up. Well, look what happens. The point 0, 0 is shifted 2 units to the left, just as we said, and then 4 units up. So the point 0, 0 on the graph of f would be mapped to the point -2, 4 on the graph of h, where h of x is the square root of x plus 2 plus 4. Another type of transformation of functions are reflections in the coordinate axes. If I want to take the graph of f of x and reflect it in the x-axis, my new function would be h of x equals minus f of x. If I wanted to take f of x and reflect it in the y-axis, my new function would be h of x is f of minus x. Let's look at some examples here. Let's start again with a basic function. F of x is the square root of x, our red graph. If I put a minus sign in front of the square root symbol, h of x is minus the square root of x. In other words, h of x is minus f of x. I get this blue graph, and I think you can see the red graph and the blue graph are reflections in the x-axis. The point 1, 1 on the graph of f would be mapped to the point 1, minus 1 on the graph of h. What if I instead replace the x with minus x under the square root sign and define g of x to be the square root of minus x? G of x graph is this black curve, and you will notice the red graph and the black graph are reflections of each other in the y-axis. The point 1, 1 on the graph of f is corresponding to the point minus 1, 1 on the graph of g. If you substitute a minus 1 for x here, then minus 1 would be 1, and the square root of 1 is 1. So the point minus 1, 1 is on the graph of g. Point 1, 1 is on the graph of f. So f and g are reflections of each other in the y-axis. So far, we've talked about horizontal and vertical shifts and reflections in the coordinate axes. These are called rigid transformations because they do not change the basic shape of a graph, only its position. Now we want to talk about non-rigid transformations that do cause a change in the shape of a graph. Vertical stretches and shrinks work really intuitively. If I take a number c greater than 1, and I define g of x to be c times f of x, g is going to be a vertical stretch of f. If I take a number c between 0 and 1 and define g of x to be c times f of x, g is going to be a vertical shrink of f. Horizontal stretches and shrinks work a little bit counterintuitively at first, but I think in a minute you'll see why they work the way they do. Here, if I take a number c between 0 and 1, and I replace x with c times x, and define g to be g of x is f of c of x, that is actually a horizontal stretch of f. If I take a number c greater than 1 and replace x with c times x, and define g of x to be f of c of x, then g is actually a horizontal shrink of f. Let's see how this works. Start with f of x is the square root of x, the red graph once again. If I define h of x to be 4 times the square root of x, I get this blue graph. The point 1, 1 on the graph of f maps to the point 1, 4 on the blue graph, the graph of h. The graph of h is a vertical stretch of the graph of f. On the other hand, if I define g of x to be 0.25 times the square root of x, in other words, 1/4 times the square root of x, I get this black graph, and the point 1, 1 on the graph of f corresponds to the point 1, 1/4 on the graph of g. So g is a vertical shrink of the graph of f. Let's talk about horizontal shrinks and horizontal stretches. This time we're going to use f of x is the sine of x. That is a trigonometric function which you may study in later math courses. But for now, just realize that this red curve is the graph of f of x equals the sine of x. If I replace x with 2x so that I have another function equal to the sine of 2x, I actually am going to have a horizontal shrink of the original function. Notice that this part of the wave from 0 to 1 back to 0 goes along an x-axis where the x value goes from 0 to pi. In the function down here, the function goes from 0 to 1 back to 0 as the x-axis goes from 0 to just pi halves. You can see that the red graph has been horizontally shrunk by replacing x with 2x. What about a horizontal stretch? Suppose I replace x with 1/2 x. Now the function goes from 0 to 1 back to 0 as x goes from 0 to 2 pi instead of 0 to pi. And you can see that I've taken the red graph and now there is a horizontal stretch of that graph. So we have talked about vertical shifts, horizontal shifts, reflections, and stretches and shrinks. I hope that you will experiment with different functions and transforming them by shifting their position or by stretching and shrinking them, and have some fun just exploring how all of these functions are affected by these different types of transformations.